continuous. So continuity of a function. A function f of z is single valued function. It defined in some neighborhood of the point z0, which includes the point z0. F of z is defined in some neighborhood and at point. F of z is defined neighborhood of the point and at the point, which includes the point. Then f of z is said to be continuous at the point z0. F of z is said to be continuous at the point z0 if for a given real number epsilon greater than 0. We can find a real number delta greater than 0. For a given epsilon greater than 0, we can find delta greater than 0, such that which is always exist for given epsilon greater than 0. In that case only f of z is said to be continuous, such that mod f of z minus f of z naught less than epsilon wherever mod z minus z naught less than delta. Okay, so that means if z is approaches to, that means if z is approaches to z naught with the delta radius, then f of z is approaches to f of z naught with the radius epsilon greater than 0. Okay, that is a common definition. If z is approaches to z naught with the radius delta greater than 0, f of z is approaches to f of z naught with epsilon greater than 0 radius. Okay na? In mathematically mod f of z minus f of z naught less than epsilon wherever mod z minus z naught less than delta. Sometimes z is equal to z naught because of which includes the point z naught. F of z is defined at the point z naught also, okay, which is must and should. F of z is must be defined at the point z naught. Okay na? In another words, this is a common definition. In another words, in mathematically, if the following three conditions are satisfied, if any function, the function is said to be continuous at the point z naught. Okay, the three conditions are: first one, f of z naught is exist, function is defined at z naught, okay, which is a finite value. F of z naught is exist. Next one, limit z tends to z naught f of z, limit is also exist. Okay, this is if limit is also finite value, functional value finite and limit value is also finite. And third one is if these two are exist, and third condition is limit value and functional value, these two are equal. That is third one, limit value and functional value at the point, these two are equal. In that case only given function is said to be continuous, otherwise is not a continuous. So otherwise is not a continuous means is a discontinuous at the point z equal to z naught. Okay, a function f of z which is not continuous at z naught is said to be discontinuous at z naught. Okay, function is continuous means at point z naught exist finite value, limit value finite, and these two are equal. That is third case. In that case only function is continuous at the point z naught, otherwise is discontinuous at the point z naught. Okay, next see here, a function f of z is said to be continuous in the domain D. Okay, a function f of z is said to be continuous on domain D, domain D is domain. If it is continuous at every point in D, function is said to be continuous in whole domain. That means f of z is continuous at every point inside D. Okay, is domain D. A function is said to be continuous in D means, on D means f of z is continuous at every point inside D. In that case only f of z is continuous on the domain D. Next one is removable singularity. Removable discontinuity. Removable discontinuity means when it is function is continuous, f of z naught exist and limit value, limit f of z at z tends to z naught is also exist. If these two are equal, function is continuous. So removable discontinuity means functional value exists, limit value exists, but f of z naught not equal to limit, Okay now, functional value exists, limit value exists, but the two are unequal. In that case, at the point z naught is called a removable discontinuity. In this case, we can redefine as a continuous function. That continuity is equal to its functional value. You should replace L by f of z naught. In this case, f of z naught is equal to L. That means the limit z tends to z and f of z naught equal to f of z naught. In this case, function is continuous. We are redefined. Okay. Next, if f of z and f of z and g of z, these two are two continuous functions. Okay, f of z and g of z are two continuous functions. Then its sum f of z plus or minus g of z and f of z into g of z are continuous. F of z, f and g are continuous at a point z naught. Then its sum and subtraction f of z plus or minus g of z and f of z into g of z product is also continuous. And division case, f of z by g of z is also continuous if g of z is not equal to 0 at z naught. Okay, now so is one proper theorem. F of z and g of z are continuous at the point z naught. Then f of z plus or minus g of z, f of z into g of z product, and division f of z by g of z, f of z by g of z is also continuous, but g of z naught is not equal to 0. G of z is not equal to 0 at z naught. If it is 0, something by 0, what will happen? It is undefined form. So that's why g of z naught is not equal to 0. Okay, na? This is the third one theorem. Next, the function f of z is continuous at z equal to infinity. Okay, see here clearly, the function f of z is continuous at z equal to infinity if the function f of 1 by z is continuous at z equal to 0. At z equal to infinity continuous, then just you should replace z by 1 by z. F of 1 by z is continuous at z equal to 0. Z equal to infinity means z equal to 0. 1 by infinity is 0. Okay, na? Okay, clear. Next, show that the functions e for z, sin z, cos z are continuous for all z. For all z means everywhere on whole complex plane. Okay, first one is f of z. So f of z equal to, let f of z equal to e power z. You know the usual notations, z equal to x plus iy and f of z equal to u plus iv. Okay, z equal to x plus y and f of z equal to u plus iv. So f of z equal to first one e power z, e power z equal to e power x plus iy, so which is equal to e power x into e power iy. We can split e power x into e power I theta value cos theta plus I sin theta. In place of theta here y, which is equal to e power x into cos y plus I into e power x into sin y. Okay, compare with u plus iv. Here u equal to real part, u equal to e power x into cos y. Next v equal to e power x into sin y. Okay, e power x into cos y and e power x into sin y. Same similarly. Okay, na? Next second one is sin z, so which is equal to sin of x plus iy. So value is equal to sin x cos hy plus I into cos x sin hy. Okay, is value. Here real part is u equal to sin x into cos hy. Imaginary part v equal to cos x into sin hy. Okay, here cos hy, here sin hy. Same similarly, third one cos z equal to u plus iv. Here u equal to z equal to x plus iy. So it's after simplification, cos z equal to cos x cos hy plus I into sin x sin hy. Okay, these are simplifications. First one is e power x into cos y u. Next, v value is e power x into sin y. In second one, sin x into cos hy, cos x into sin hy. Third one, cos x into cos hy, sin x into sin hy. You see here, in each case u comma v are, in three cases u comma v are real valued functions. real valued functions of two variables x and y. Is it right or wrong? In three cases, u comma v are real valued functions of two variables x and y. You know, e for x, is it continuous or not? In real case, is always continuous. Trigonometric functions, is it continuous graph or not? If you draw the curve to the function, is it continuous or not? E for x, continuous graph. Cos y, continuous. E for x, continuous. Sin y, continuous. Okay. Product of two continuous functions is also continuous in last one theorem statement. If f and g are continuous, then its product is also continuous. Similarly, is one function. The product is also continuous. Its product is also continuous. Okay. U comma v are everywhere continuous. Similarly, sin x cos hy. Sin x is trigonometric function, cos hy hyperbolic function. Hyperbolic functions are always continuous. Trigonometric functions also continuous functions. If you draw the curve to the given functions, are they continuous graph or any breaks? There is no break because of the curve of the sin x and cos hy. Okay, these two are continuous functions. Product is also continuous. These two are continuous function. Product is also continuous. Similarly, these two are also continuous. These two are also continuous. Product is also continuous. Addition of two continuous functions is also continuous because of last statement. F and g are continuous, then f plus or minus g is also continuous. But here adding, these two are continuous. Same, these two are addition is also continuous. Okay, na? In the first case, in this case, addition is also continuous. Okay, na? In three cases, functions are continuous. Real value function of two variables are continuous, and hence the complex valued function, complex valued variable function or valued function z are continuous for all z. Okay, na? This is the procedure. Okay. See here one problem. Show that the function f of z is not continuous at z equal to 0, where f of z equal to real part of z square by mod z square. At z not equal to 0, otherwise 0. Okay, only z not equal to 0, that value is function. Okay, if it is otherwise means z equal to 0 case, z equal to 0, that value is 0. Okay, show that the function is not continuous, which is not continuous. Show that. Okay, first f of z equal to real part of z square. Real part of z square value is, sir, I will write real part of z square by mod z square. Okay, z equal to x plus iy, which implies z square equal to x plus iy whole square, which is equal to x square a plus b whole square plus y square. Y square value I into y whole square. I square value minus 1 y square plus 2i x y. In this case, real value is u equal to real part. Real part is x square minus y square. V is imaginary part, that value is 2xy, not I. I coefficient is imaginary part. Okay, na? Here u equal to x square minus y square, v equal to 2xy. Okay, real part of z square equal to x square minus y square, Next, mod z square values, under root of x square plus y square. You know that whole power 2, square and root will be cancelled, only you will get x square plus y square. Okay, na? Now I am going to determine the limit value. If a limit is when the function is continuous, function value f of z naught is exist, and limit f of z at z tends to z naught is exist, and these two are equal. In this case only function is continuous. Just I am determining the f of z naught value, f of 0, because of z naught equal to 0. Okay, f of z naught equal to, so depend in the given function, that value is 0. At z equal to 0, function value is 0. Okay, na? Z equal to 0, function value is here, f of z naught value is 0, and finding the limit z tends to 0, f of z value is real part of z square by mod z whole square, which is equal to limit z tends to 0, Okay, real part of z square value x square minus y square by x square plus y square. Limit x tends to 0, y tends to 0, x square minus y square by x square plus y square. Okay, along the path along the path z y equal to mx, because of z tends to 0, z tends to 0 means passes through the origin. The straight line passes through the origin. Just I'm treating the taking the along the path. Path means a straight line. Y equal to mx. Just I'm substituting y equal to mx in the given limit, given function. That is limit x tends to 0, x square minus mx whole square by x square plus mx whole square. In this two terms, x square will be common. Numerator denominator same term will be common. That will be cancelled. You will get limit x tends to 0, 1 minus m square by 1 plus m square, which is equal to, after substituting x tends to 0, there is no x. So finally we will get the 1 minus m square by 1 plus m square is the limit. Okay, which depends on m value, depends on m. Okay, so different values of m, different values, different values of m having different limits, different limits. Okay, if limit is exist, that is unique. Okay, if limit is exist, that is unique, but here different values of m having different limits, so therefore limit does not exist, limit does not exist. If limit is exist and function value limit value is equal, then function is continuous, but here limit is does not exist, and hence function is not continuous. Okay, function is not continuous. Okay, now if limit is exist, and third case limit and function value are equal, in that case when the function is continuous at the point, but here limit is does not, second case is failed, therefore function is not continuous at the point z equal to 0. Okay, this is the procedure to determine is the function is continuous or not continuous. Okay, now it's clear.